Look at your own hand. It is constructed entirely of atoms, and inside those atoms, negative electrons surround a dense, positive nucleus. By the most basic rules of physics, opposite charges attract. Those electrons should instantly crash into the center, collapsing the atom entirely. Technically, you shouldn't exist. That electrostatic pull never rests. It acts as a constant drag, continuously drawing the negative charge toward the positive core. Yet, at the turn of the 20th century, the scientific establishment wasn't worrying about this impending collapse. They were operating in an era of absolute certainty. Isaac Newton's laws of motion had masterfully mapped the mechanics of the physical world. His math explained exactly why an apple falls to the Earth and how planets maintain predictable orbits around the Sun. Decades later, James Clerk Maxwell unified electricity, magnetism, and light into a single elegant set of equations. The consensus was clear. The universe was a perfectly solved, deterministic machine. Just a few small clouds remained on a perfectly clear scientific horizon, but a single microscopic anomaly regarding the internal structure of the atom was about to unravel that entire framework. The crisis began in 1909, when Ernest Rutherford and his team fired heavy alpha particles at a sheet of gold foil just a few hundred atoms thick. This visualization maps their shocking result. Most particles pass straight through the foil, but a tiny fraction violently ricocheted backward. The atom was almost entirely empty space, anchored by an impossibly dense microscopic positive core. Rutherford proposed a new planetary model. The atom operated like a miniature solar system, with negative electrons orbiting the positive nucleus across vast open distances. But applying Maxwell's established laws of electromagnetism to this picture ruined it. The rules stated clearly that any electrical charge moving with acceleration must continuously emit electromagnetic radiation. Even if an electron maintains a steady speed, moving in a circle requires a continuous change in direction. That directional change is a form of acceleration. Therefore, the orbiting electron is forced to bleed energy out into space. As the electron loses energy, it slows down. It can no longer fight the nucleus's electrostatic pull, dragging it into a tighter orbit. To stay aloft at a lower altitude, it has to move faster, which increases its acceleration, causing it to bleed energy even quicker. Calculations based on classical physics showed this death spiral is inescapable. It would take precisely 1/1000th of a second for the electron to crash into the core. If that math were accurate, every atom in the universe would have collapsed the moment it formed. The persistent existence of the matter all around us proved that the macro-world laws of physics simply do not function inside the atom. A new set of rules was required to explain reality. In 1913, a young Danish physicist named Niels Bohr stepped in with a radical proposal. To stop the collapse, he introduced the concept of stationary states. Bohr essentially issued a decree that electrons were strictly forbidden from radiating energy as long as they remained in specific, stable orbits. He argued that electrons can only exist in quantized energy levels. They absorb or emit energy by instantaneously jumping between these separated tracks, dropping a single photon on their way down. This model matched experimental observations of atomic light emission perfectly, but it was an arbitrary mathematical patch. It offered zero explanation for why these rules applied. A true explanation didn't arrive until the mid-1920s, driven by figures like Werner Heisenberg and Erwin Schrödinger. They required killing the idea of the planetary orbit entirely. Under true quantum mechanics, the electron is not a physical dot traveling on a set track. It behaves as a continuous wave, a smeared probability cloud occupying the space around the nucleus. You can never pinpoint the exact location and velocity of an electron at the same time. You can only calculate the mathematical likelihood of finding it in a given area. The building blocks of reality aren't tiny, solid objects moving through empty space. They are localized zones of inherent uncertainty. This shifts our understanding of the atom entirely. It is not a piece of static architecture, but an arena for a violent, continuous tug of war between two opposing forces. This diagram shows the inward force. The positive nucleus constantly exerts electrostatic potential energy, trying to drag the negative electron cloud inward to crush it. But as the cloud compresses, it triggers a reaction dictated by the Heisenberg uncertainty principle. It acts as an outward quantum pressure. By forcing the electron into a smaller physical space, its location becomes far more certain. Because of the rules of quantum mechanics, that increased certainty causes its momentum and kinetic energy to skyrocket. The kinetic energy pushes back. The cloud expands until the inward electrostatic pull and the outward quantum pressure reach an exact, unyielding equilibrium. This specific geometric sweet spot is the atom's ground state. We can test the strength of this balance by pushing a material to its absolute thermal limit, freezing it down to 0 Kelvin. At absolute zero, the atoms themselves lose their thermal heat and lock into a motionless lattice. But the internal quantum motion never stops. The electron clouds maintain maximum kinetic energy to resist the electrostatic pull, existing as zero-point energy. Matter never truly rests. The physical solidity of all the world, the chair you sit on, the floor beneath you, the flesh of your own hands, is an illusion held together entirely by the inescapable tension of quantum vibration.